right, we're going to change topics a little bit here, and we're going to talk about phase diagram. So what is a phase diagram? It's a graphical presentation summarizing the conditions under what, as to which state a compound is depending on the particular temperature and pressure. So the diagram is divided into areas that represent each state of the substance. So what we do basically is we plot temperature and pressure on the two axes. And then you'll see the curves separating each area will be the boundaries, and that's where the phase changes happen. So this is a typical phase diagram for a single substance. It's got three different curves that divide the diagram into the solid, liquid, and gas region. So generally the solid is at the lower temperature, liquid is in the middle, and gas at the higher temperature. And you can see that pressure also will change. So let's look at the different parts of a phase diagram. Okay, so curve AB is the solid liquid line. And so if you're on the point, if you're on that line, then you're at the melting point and you have both solid and liquid present. If you're to the left of that line, you're only on a solid. If you're to the right of the line, you're a liquid. But if you're on the line, you're in the melting at that specific temperature and pressure. So you can, you read over the pressure and you can find the temperature at that particular melting point. And notice because the line is pretty steep, temperature, the freezing point temperature doesn't change much with pressure, as we said earlier. If the liquid is more dense than its solid, which is not very usual, that actually happens to be true for water and not very many other things. But if the liquid is more dense than its solid, then the curve will lean slightly to the left, which means that the melting point will decrease with pressure, just slightly. With most things, if the liquid is less dense than the solid, and again, that's most of the time, but water being a critical exception to this, the curve will lean slightly to the right, which means that the melting point will increase slightly with pressure. Again, water, so you can tell which one's more dense by which way it's leaning. All right, the curve AC then divides the liquid region from the gaseous region. And so if you're on the line AC, then you're at the boiling point for a particular pressure and temperature. And notice that because that is a longer, kind of thinner, lower slope, temperature will change. The boiling point will change quite a bit depending on temperature because of the gas phase. So you can see that if pressure decreases, the boiling point will also decrease. The temperature of the boiling point will also decrease because you're moving to the left. Curve AD then divides the solid region from the gaseous region, and so it represents the sublimation points. So if you're on the line, you'll have both solid and gas present, which is the sublimation point. And again, you have a vapor pressure. If you have a solid that sublimates, then you'll have a vapor pressure building because as long as you have vapor present, you'll have a vapor pressure. That point A, which is where all three lines intersect, is called the triple point, and that happens to be the particular pressure and temperature where you can have all three phases existing at the same time. They're all three in equilibrium. So this happens to be, and note it's not to scale, but it is the phase diagram for water. And so we can see that at 1 atmosphere pressure, the dotted line goes across, and then if you read the temperature where the AB line crosses it, that would be 0 degrees Celsius. That is the normal freezing point. And then the dotted line going all the way over to the gas liquid line, AC, that would be the normal boiling point because that's at 1 atmosphere. But note that if you're at a lower pressure, the freezing point of water will actually go up slightly, but the boiling point of water at a lower pressure will actually come down somewhat. If you increase the pressure, the freezing point of water will go up slightly. If you increase the pressure, the vapor pressure will be higher for the liquid. Or if you increase the atmospheric pressure, your boiling point will increase. And then also see that point A is at 0.01 degrees Celsius and 0.006. So you have to be at kind of low atmospheric pressure to have all three, solid, liquid, and gas in present. We'll talk about point C in just a second. Here's some other phase diagrams. The one on the left is the phase diagram for carbon dioxide. So notice that actually at 1 atmosphere pressure, notice that the line intersects with the solid gas line, which is sublimation, and so that's why carbon dioxide, dry ice, sublimates rather than turns into a liquid, rather than melts, because at 1 degree atmosphere, the liquid only appears at a much higher pressure, above 5 atmospheres pressure. You don't have liquid below that. So at normal pressures, normal atmospheric pressure, carbon dioxide solid will sublimate, and that the sublimation point is negative 78 degrees Celsius. Sometimes when we have different solid phases, for example, sulfur can be in either a rhombic solid phase or a monoclinic phase. You can see the shapes over to the left. And so again, depending on pressure and temperature, it may be in a different phase. So these phase diagrams can get a little bit complicated. And so we can have different triple points depending on different solids. But we're not going to get too complex with this. Okay, so finally, point C is called the critical temperature, and this is the temperature above which the liquid state no longer exists. You only can have gaseous phase above that critical temperature. So let's just talk in general, practice problem. So here is the phase diagram for compound X. The triple point of X is negative 25 degrees Celsius and 0.5 atmospheres. So I've kind of lined up, since it's not really to scale, I've tried to create a little scale though. So I've put 0.5 atmospheres on the graph, and and negative 25.1 degrees Celsius. Also notice that the critical point is at 22 degrees Celsius and 21.3 atmospheres. So we kind of have a little bit of gauge there. So first of all, notice where point A is. What is the state at point A? Well, it should be a gas, correct? Because it's over in the yellow area. Okay, so what will happen if we decrease the temperature at A? So that's at about 22 degrees Celsius. And if we decrease it to negative 28 degrees Celsius while holding the pressure constant. So if you start at A and you kind of draw a line that is going straight to the left, you'll cross over the boiling point line, and if you get to negative 28.2, notice that the freeze, you see where negative 25.1 is. If you keep going all the way to negative 28.2, you're going to be in the solid section, so you'll be in the kind of the pink section. So if you take A and you cool it all the way down at the same pressure that it already is at, all the way down to negative 28, you'll be in the pinkish reddish section, and you will have a solid. Okay, what if we take the compound starting under the conditions of part B? So we have that solid sort of across from where A is, and then we increase the temperature back to 15.3 degrees. So if you do that, you're in the orange. So you're at 15.3 degrees. You're in the orange section. But then what if we then also decrease the pressure down to 0.002? So now you're going way, way down, and you'll be back into the yellow. So what will the state be? You'll be back in the gaseous phase at very low pressures. Okay, question D, would it be possible to make the compound starting under the condition of part C a solid by increasing just the pressure? Probably, because the critical The critical point of A is, or I'm sorry, the critical point for X is 22 degrees. So if you increase the pressure at 15 degrees, you should be able to make it a solid. It's hard to see. It's sort of hard to predict what will happen, but eventually you could cross over into the solid phase. All right, so let's talk a little bit about the properties, some properties of liquids, including surface tension and viscosity. All right, so we haven't talked yet about intermolecular forces, which we're going to get to in a second, but right at the end of first semester, we talk about the molecular structure of a substance, and we determine if a molecule is polar or nonpolar. And so the structure of the molecule and then the polarity of a molecule will help define what type of intermolecular forces will hold all these molecules together. The strength of these intermolecular forces then will affect the different physical properties of a substance, whether it's in the gas, liquid, or solid phase, but particularly right now we're talking about liquids. So these physical properties of substances are determined by the type of intermolecular force, and the type of intermolecular force is determined by the structure and the polarity of a molecule. So we're going to look at some of these physical properties. Two of the properties that we've already actually looked at, which are determined by molecular structure and intermolecular forces, are vapor pressure and boiling point. Remember that the stronger the attraction between molecules, the lower the vapor pressure, because molecules will be really hard to pull apart the stronger that they are. So vapor pressure will be lower. And then if the vapor pressure, if it's very strong intermolecular forces, then the vapor pressure is low. That means the boiling point is high, because it will take a whole lot more energy to pull those molecules apart in order to boil them. There's other physical properties that we're going to look at now. So two additional properties are surface tension of liquids and viscosity. So first of all, surface tension. Surface tension is just technically defined as the energy required to increase the surface area of a liquid by a unit amount, which is sort of hard to imagine what we're talking about. But basically, surface tension is you've seen it before. If you try to lay a penny on the top of a water, you can do that. Or we've seen these bugs that kind of stand on the top of water, and that's because of surface tension. So if you look at the picture here, a molecule that is within a liquid, in the center of the liquid, has attraction to molecules all around it. And so there's actually they're pulled equally and opposite in different directions. But if you have a molecule on the surface, the attraction to other liquid molecules will actually pull that molecule down, but there's nothing above it to counteract that. And so what happens is that the surface molecules will actually be pulled in a little bit tighter on the top than they will be in the center. And so that's what creates sort of a surface, like a sort of a filmy surface, or a tension on the top surface of a liquid. So surface tension is technically the amount of energy needed to reverse this tendency toward reduction, or the pulling down. So surface tension is actually the amount of energy needed to undo that. But we can think of a surface as the surface tension as that sort of skin, or a little bit more closely held together molecules on a surface of a liquid. So the reason why water beads up is because, again, of this surface tension. So rainwater will bead up on a waxy surface, for example, because, again, the innermost molecules are being pulled in all directions, but the surface molecules are being pulled just a little bit harder inside than out, and so they form this beading. You can see that the sphere has a smallest possible surface area to volume ratio, and so it gets pulled in. And you can see here the dropping of the the water will form into sort of a spherical thing. I'm not going to read all through this. The main thing is just that beading is affected by surface tension. And then, like I said earlier, you can lay a pin or a penny sometimes on top of water because it has a high surface tension. Or the reason why bugs can kind of skim across the water is because water has a high surface tension. Even if things are more dense than water, they may float because of the surface tension. Okay, another property of a liquid, another physical property is called viscosity. And viscosity is defined as the resistance to flow exhibited by all liquids and gases. So we can look at the picture to the right and we can illustrate it. So we kind of assume that the two beads were put in at the same time. The one on the right, because the liquid is much less viscous, doesn't keep the bead from falling, and so it falls very quickly, whereas the left is a much more viscous solution and it slows the falling of the bead more. And so that's one way that you can measure the viscosity of something. And syrup has a greater viscosity than water. And why is that? It's because the molecules are being held together more tightly in the more viscous liquid than in a less viscous. So as intermolecular forces or intermolecular attractions increase, viscosity will increase.